Good evening to all of you. Today we'll discuss regarding the one new phenomenon, the buoyancy phenomenon. So whenever the solid body is immersed in the liquid, so one net upward force is acting over the body. What is the reason of this? The reason is the solid body displays some amount of the liquid, and this liquid having some weight, this weight is acting over it in the opposite direction, upward direction. But this weight is concept is coming from the hydrostatic pressure. How it is coming, we'll see. So we coming to the slide first. What is the source of the buoyancy force and where it is acting, the buoyancy force. We'll see first these two concepts, and then we'll go for the stability. We'll analyze the stability, whether the body is fully immersed in the liquid or it is floating. Two concepts. So either submerged body or floating. So in case of the submerged body, the weight of the body is more than the upward force or buoyant force. That's why it gets submerged inside the liquid. Whenever the weight and the buoyancy force is the same, the body will float over the liquid. The concept of the floating will come there. So we'll see one by one in this chapter regarding the buoyancy force. So we come directly to the slide here. How the buoyancy force is acting. And this phenomenon is known as the buoyancy. So in that case, if you consider here one free surface and you see here, considering one free surface. That is a free surface. So free surface it is, and the depth along this depth is the z-axis. Okay. Now one solid body, if you consider one solid body is here submerged condition. So you consider one's arbitrary solid body is submerged condition. Now, what are the forces acting over it? One force is, definitely it having some weight, so weight will act in the downward side. So one weight is there. So it is at this position. So what are the other forces acting over it? Something is there. Weight is always acting downwards. So there must be some force upwards to make this body at an equilibrium condition at the same position, same location. Something is acting over it, and that is upward. And that's why it nullifies the weight and keep its own position. It is under equilibrium condition at here. So what is that upward force concept? Something upward force is acting over it, which neutralize the weight. This force is buoyancy force. And what is that force? What is the source of this force? We'll see now. So this arbitrary body, you can consider this arbitrary body a number of, here one area you consider, and the same area here. So one elemental volume you consider here, elemental volume. So this is nothing but we are telling it sometimes that is the one particle, it's as it is a particle prism. This elemental particle prism. So this solid body is number of vertical prisms. This solid body is number of vertical prisms. So the top portion from the free surface, the top portion is at height of 0. And the bottom portion is the height of the Z2. And Z2 minus Z1, the height of the vertical prism is Z. That is our consideration. So vertical prism is there one volume, that is P, AZ, and height of it. Same here, same area is there. Height is Z. So total volume you can consider for the vertical prism Z into A. That is the consideration. Now, you know the free surface water, as there is a water over it, water or any other liquid. So at the free surface, there is atmospheric pressure. If you go down at the depth from the free surface, pressure will be rise. So here, if you take it A, B, or 1, 2, whatever you were saying. So at A, the pressure, the force due to the pressure, the force is acting due to the pressure, EFA. And that is downwards. And here, the force is acting due to the pressure, DFP. So what is DFA? What is DFP? We have to see now. This force is due to the pressure. So DFA, the pressure at A, what is the pressure? Into DAZ. So at A, what is the pressure? Atmospheric pressure plus rho G Z1. No doubt. Atmospheric pressure because you are going down depth. So your hydrostatic law, if you remember, there was written as dP by dZ is equal to minus rho G. This was the hydrostatic. So from here we get this equation. P, if you go by depth, so P is equal to P atmospheric into rho G Z at the height of the jet. That is here we are considering, nothing but. So we consider this thing only here, nothing else. So just a hydrostatic law, we are directly written here this formula. Next we'll see the DFB. So DFB will be the similarly the same way, that will be DFB is equal to PB. It is the same at the top and the bottom. Whatever the vertical prism we are choosing, area we are keeping same. So P atmospheric plus rho GZ2 into DA. So which is bigger in here? We clearly see that Z2 is much more bigger than Z1. So DFB will be greater than DF1. So the net upward force is acting over the vertical elemental prism. The net upward force over the vertical elemental prism is DFB minus DF. So that is the net force is acting over it. So net force we can see, that is the acting over it. We are rewriting this thing one more time. So DFP minus DF is the net force is acting over the vertical prism. And what is that? That is nothing but rho G Z2 minus Z1 into DAZ. Z2 minus Z1 you have already seen, rho G Z AZ. ZA DAZ is nothing but the elemental volume of the vertical prism. So the total net force, net upward force, that is nothing but DFB minus DF. Net upward force will be rho G. Rho and G is because the volume is the arbitrary volume you have considered here. So rho G is not depends on it, and it will come out of the integration. So remaining part will be this. So the net force is acting rho, density of the fluid, keep it in mind, this rho is the density of the fluid. Because hydrostatic law, this rho, we are taking this rho from the hydrostatic law. And this is coming from the density of the fluid, not the solid. Keep this thing in mind. Density of the fluid, gravitational acceleration, and the volume. Total volume of the arbitrary substance. So V is the volume of the solid body, or we can say the same volume of liquid will be displaced by the same solid body. So V, better to write it that the volume of liquid, because that is the same thing, same volume, because the solid will acquire the same volume. How much amount of the liquid will be displaced, the same volume will be acquired by the solid body. Volume will not change. So volume of the liquid displaced by solid body. So this net force can be better to write it in this way. This net force, upward thrust or net force, better to write it that the weight of the, because you see density into volume is giving it the mass, mass into G is the weight. So weight of the liquid displaced by solid body, which is immersed in the liquid, or submerged in the liquid in such a way. It may be floating condition also. Now two condition we'll see, two types of the things we'll see it later. That is the one is the submerged condition. So inside the liquid is submerged condition. In the submerged condition, if you keep a position, it is submerged at here. There is a free surface. Let you take it as a free surface. It is submerged in this position. So in this position, whatever the weight is acting over it, in this position, whatever the W is acting, and over the body another force is acting, upward force, that is the FP or buoyancy force. In that case, W is slightly greater than the FP. That's why the body is getting submerged. But floating condition, we'll see later next also. The floating condition, this W is equal to FP always. So the W and the buoyancy force, buoyant force, this FP is another name is the buoyant force. Both are the same and nullify each other. That's why it is floating over the liquid. So this is the concept of the submerged condition and floating condition. So this thing is coming from the Archimedes principle. Archimedes is telling that the buoyant force, about the buoyant force and the phenomenon is known as the buoyancy phenomenon. This buoyancy phenomenon is coming because of the difference in density between the liquid and the solid. And what is the amount of the force will be acting over it? The amount of the force is nothing but the weight of the displaced liquid by the same solid body. This principle is coming from the Archimedes principle. This thing you might have. So this phenomenon is the Archimedes principle. This principle. From class 7-8, you might have heard this thing. But now we'll discuss the thing where this force is acting. Where this force is acting. That is the concern for us. So previously we are considering here, sorry. So here is a free surface and arbitrary body we are considering. This direction is the Z direction. This is the X direction we are taking. So over the body, initially what we are considering, one vertical prism was considering in this way. And over the vertical prism, what is the force is acting? DFB. Buoyant forces, net buoyant force. Net, sorry, we have taken it in this way, so don't need to be confused with it. So DFA, DFB, so net force was acting over it, DFA. So that is the net force. Net force was acting over it. So that was the net force was acting over it. And what was the value came? Rho G. So net force is the upward force. So net force is the upward force. So if you consider here the net force, so net force is the upward force is acting, that is the DF net. And the distance from the, where it is acting in here, so distance is the X. So the moment due to the force, will be X into EF net. That is X rho G, moment due to the buoyancy force about the Z axis. Moment about Z axis. If you integrate this thing, from the Varignon's theorem, if you remember from the Varignon's theorem, the net force, the moment due to the resultant force about the same axis. So where is the resultant force is acting? Here, the resultant force is acting at somewhere in the centroid. Somewhere here. There is a resultant force is acting that you take here. Here is the net FB is acting. Net F net is acting. Net force is acting. Net force, if you remember what is the net force was we have written, after integration we are getting that rho G. So F net into XB. So F net is acting at the point, the distance from the Z axis, this point, the distance from the Z axis is XB. This is nothing but the center of buoyancy. So XB denotes the X distance from the Z axis, the X coordinate of the center of buoyancy. So in this way, we are getting the center of buoyancy here. So XB is equal to rho Gx Phi divided by F net. So that is nothing but in this way rho G X divided by rho G. It would be out of the integration, sorry. It should not be inside the integration. This part will be out of the integration. So better to write it. I rewrite this thing one more time. So better to do in this way, because otherwise logarithm term will come, but it will not appear. So no log term will come here. So XB, we rewrite this equation XB in this way. The XB is equal to 1 by F net, that is nothing but rho B into out of the integration rho G X. So 1 by V X of this way. X. So that is the x coordinate of the center of buoyancy. In the physical concept of the center of buoyancy is nothing but the center of buoyancy is the centroid of the displaced liquid. Center of buoyancy is nothing but center of buoyancy is the centroid of or center of gravity CG of liquid displaced by because the buoyancy force, net buoyancy force, FB, you can write it here, it will be double right, that's why FB I'm not taking, F net only writing. The buoyancy force is nothing but the weight of the displaced liquid. So where it will be at? The center of gravity of the displaced liquid. So that is it. This is known as the center of buoyancy. The center of buoyancy is nothing but the center of gravity of the liquid displaced by the solid body, which is immersed in the liquid. That's why we are defining it here. So concept is here.